in this problem, we see a solenoid, and inside the solenoid there is another coil of wires. So now, in this problem, do you see the direction of the currents of the solenoid wires have been indicated here? So basically, it's you can use now the right hand grip rule to find out what's the direction of the magnetic field it's gonna be inside the solenoid because of the current I flowing through the solenoid wires. Now in part A, they have given you the temporal current, which is basically 70 amperes, right? So this basically means that with time, your current is increasing, right? So if I say this I, so with time, my current is increasing, right? And it's increasing linearly. Now, for what's the magnetic field because of this current inside the solenoid? Now we know that for the solenoid, the magnetic field formula is mu naught n I. In this case, your n is the wire, the turn density. In this case, this is 200 turns per meter that's given here. And your I is basically 7t, right? And mu naught is a constant. So if you just plug in the values, you'll find that your B inside the solenoid is basically 1.759 millitesla, right? And it's a function of T, right? Because your current is a function of T. Now, remember that since current is increasing linearly, your B should also increase linearly in this case, right? So now this is very important because now in part B, they have asked you to find out the direction of the induced current inside the coil, right? So basically you have to find out the direction of the current for this loop of turns, right? For the internal coil. Now remember that now if we use, let's say if we use the right hand grip rule for the current directions for the solenoid for these currents, right? So if we use the right hand grip rule, so we find that our thumb is pointing in this direction, right? So basically for the solenoid, the current direction shown, the solenoid will generate a magnetic field in this direction, right? And remember, with time, the magnetic field is also increasing, right? With time, the magnetic field is also increasing. So now what will happen is that since the magnetic field is increasing with time in the right hand direction, according to Lenz's law, right? Because Lenz's law tells you like this is the Faraday's law, right? So this is the Faraday's law. Now this negative direction is because of the Lenz's law, right? So this basically tells you that the direction of the induced voltage or the current is will try to reduce the change that's causing its induction, right? So since the magnetic field is increasing with time on the right hand direction, the induced current in this coil will be such that to reduce the increase on the right hand direction of the magnetic field, right? So therefore the magnetic field of the induced magnetic field will be on the opposite direction, right? So now what will be the current direction? So let's see that, okay, so this is my solenoid, right? If this is my solenoid, right? So the direction is given like that. So now for this direction of the current of the solenoid, my magnetic field is generated on the right hand direction, right? But for the coil, the current would flow such that it will generate an opposite magnetic field, right? So if you apply the right hand grip rule, right? So then you'll see that the current direction for this left magnetic field should be oppositely flowing, right? So it will be cross here, dot here, right? So that will give you an induced magnetic field direction such that to reduce this increasing change, right? So that's basically coming from the Lenz's law. Now for part C, it's asked you to find the magnitude of the induced EMF in the coil C, right? So since you're looking for the magnitude of the induced EMF, so I'll just do the modulus, right? And so that's my Faraday's law, right? That's my Faraday's law. Now for this one, so for this one, what's my the value of N, right? So N is basically this phi b is because of the magnetic field, the original magnetic field B, right, times the area, right? Now which area? Area of the coil, right? The area of the coil. So basically that this magnetic field, the magnetic field that's flowing through this area of the coil will be given by, will determine your phi b, right? So phi b is basically B times A. Right. So now you know the radius of the internal uh, loop coil, right? So that's like 0.7 millimeter. So this area, okay. So let's proceed from here. So now, if you plug in the values, we know that the number of turns N in this case is just 200, right? It's given for the internal wire, so it's 200, right? So and we know from here that my magnetic field is a variable of time, right? So what I could do is just plug in this value, right? So I just plug in this value. So d phi, so it's like b dot a, right? It's ba phi b. So I'll just plug in the magnetic field value into 10 power minus 3, right? It's a variable of time, right? Times area, right? Now area is the area of the coil, right? The internal coil, remember, because that's where the induction is happening. So that's like pi r squared, right? So now what's the radius of the internal coil? It's 0.7 millimeter, right? So I'll just consider this as meter. So I'll just consider, right? So that's basically 200, and this is d by dt times this with the variable of t, right? So basically that will give me just this value. So it's just 200 times 1.759 millitesla times pi 0.7 by 1000 squared, right? So that's the amount of induced voltage that I'm getting.